Start. Hello. Our group, which comprises of me, Tarun, Prashik, Ajay, and Ravish, have been assigned to perform the experiment on photoelectric effect. Before we begin our experiments, let's get an idea about photoelectric effect, and it's about history. The first part about photon and photoelectric effect is going to be explained by my friend Prashik. So, Prashik, here you start.
Hello. So here first we are going through photoelectric effect. The word photoelectric effect is made up of two words, photo, which here means photons, and electric, which here means current. So photoelectric effect means currents due to photons. Next. What is photon? A photon is a type of elementary particle that is the quantum of electromagnetic field, including electromagnetic radiation such as light and radio waves, and the force carrier for the electromagnetic force. The photon has no charge, no resting mass, and travels at a speed of light. Next, here is the theory of photoelectric effect, and the diagram depicts the working of photoelectric effect. When a beam of light of sufficient high frequency incidents onto a clean metal surface, then the light will cause electron to leave the surface. The definition of photoelectric effect is the phenomenon of emission of electron by the metals when they are exposed to light of suitable frequency is called as photoelectric effect. An emitted electron is called as photoelectron. Next please. The ejection of electron from the metal surface when the light of suitable frequency is allowed to fall on the surface. This suitable frequency is called as threshold frequency, which means minimum frequency, and the corresponding wavelength is called as threshold wavelength, which means maximum wavelength. Work function. The work function is the energy required to remove an electron from the highest field level in the Fermi distribution of a solid. The formula for work function is W equals to h nu naught, where h is Planck constant and nu naught is frequency. Next, please. Cutoff frequency. So here the graph depicts the frequency of incident light versus stopping potential. It also explains the when the frequency of incident light increases, the stopping potential also increases. To have a photo emission, the frequency of incident light should be more than some minimum frequency. This minimum frequency is called the threshold frequency or cutoff frequency. When photon incident on a metal during interaction with an electron totally gets absorbed if its frequency is greater than threshold frequency, or otherwise it does not lose energy at all. Next please. Different materials have different cutoff frequency. The figure depicts the value of cesium around have a cutoff frequency around 4.9, potassium has cutoff frequency at 4.5.45, sodium has 5.5, lithium has cutoff frequency around 5.9. Next please. Corresponding to frequency, we can find wavelength below which only photoelectric effect will be shown. For copper, cutoff wavelength is 571 nanometer. For sodium, the cutoff wavelength is 504 nanometer. For zinc, the cutoff wavelength is 310 nanometer, and for platinum, cutoff wavelength is 220 nanometer. Thank you.
Hello, Tarun again. In the previous part of the video, my friend Prashik has explained about photon and photoelectric effect. He ended with cutoff wavelength. Let's see this in virtual lab simulation. Let's select sodium. We know that the cutoff wavelength of sodium is 504 nanometer. Now, no matter what other conditions are, sodium will not show photoelectric effect above 504 nanometer. So let's see. Let's first see for a wavelength which is less than 504 nanometer at which the sodium should see photoelectric effect. So if we increase the intensity, you can see that the current is increasing and we can see the photoelectrons coming. So now as this wavelength is less than 504 nanometer, photoelectric effect is being shown. Now if we increase this wavelength above 504 meter, then you can see that the current value drops to 0 and the photoelectrons are not coming out. Now, even if we increase the intensity to 100%, then also photoelectrons are not going to come out. Or even if we change our voltage to 8 volt, which is the maximum which is possible in the slab, then also we will not able to see photoelectric effect. So you can see at even at 8 volt the photo current is still zero. So wavelength below 504 nanometer is the only wavelength at which photoelectric effect will be shown. So now we are familiar with the terminologies related to photoelectric effect. Now we see how photoelectric effect was discovered. We will go into its history and it is going to explain by my friend Ajay. So Ajay, you can start.
Now the history of photoelectric effect. Photoelectric history is based upon Max Planck's theory of blackbody radiation and his hypothesis, and Einstein's contribution. Einstein here theorized that the energy in each quantum of light was equal to the frequency multiplied by a constant, later called Planck's constant. Now, what are the hypotheses given by Planck's? Let's see them. Here, the Planck's explain the energy distribution curves of blackbody or cavity radiation in year 1900 at the Academy of Science in Berlin. There he suggested that the walls of cavity emitting radiations are made up of electric dipoles. According to their temperatures, different dipoles oscillate with different frequencies and emits radiations of frequencies equal to the frequency of their oscillations. Now, according to the classical physics, an oscillator may possess any amount of energy that an oscillator may acquire continuously varying energy which varies from 0 to the maximum available. For that, Planck presented a revolutionary idea that these microscopic oscillators may not possess any arbitrary energy as allowed by laws of classical mechanics. If vibrational frequency of such oscillator is assumed to be f, and then the energy given by is E equal to nhf, where n is any integer from 1 to infinity. This equation also suggests that energy of an oscillator of frequency f is hf, 2hf, and 3hf, and so on. Thus, energy of microscopic oscillator is an integral multiple of hf. In other words, the smallest quantum of energy of an oscillator of frequency f is hf. This small bundle or packet of energy is known as photon. Now, the photoelectric effect was basically discovered accidentally by H. Hertz in 1887 during his study on the emission of electromagnetic waves by the means of spark discharge. In this experiment, electromagnetic waves from the transmitter antenna induce a potential difference across the spark gaps. As evidence from the jumping spark across it, Hus noticed that spark jump more when the cathode was illuminated by ultraviolet light. This observation suggested that light facilitated the escape of charge from cathode across the spark gaps. Now, the details of photoelectric effect were studied by the P. Leonard, one of the students of Hertz. The experimental arrangement to study the photoelectric effect is shown in figure 7.2. The ultraviolet light entering from quartz window is incident on a clean photosensitive surface S. Here C is collector while S is cathode. C can be kept at different positive or negative voltages with respect to S. And by this, we can understand the characteristic of photoelectric effect in reference to frequency and intensity of incident light, and also in terms of number of photoelectron emitted and their maximum kinetic energy. When the collector is positive with respect to S, the photoelectrons are attracted to it, and microemitter registers a current. Now the amount of current passing through the emitter gives idea about number of photoelectrons which were coming out. Now at some point of value of potential difference, when all emitted electrons are collected, increasing the potential difference further has no effect on current. Again, when the collector is made negative with respect to S, the emitted electrons are repelled, and only those electrons which have sufficient kinetic energy to overcome this repulsion may reach the collector and constitute in current. So emitter current falls. On making collector more negative, number of photoelectrons reaching to the collector decreases. Now, for a particular value of potential, the photoelectrons are unable to reach the collector and current becomes zero. It remains zero even after it made further negative than specific value of negative potential. This minimum specific negative potential of collector with respect to emitter at which photocurrent becomes zero is known as stopping potential for given surface. Leonard performed further experiments by varying intensity of light and measured maximum kinetic energy, the number of electrons via photocurrent. He found that by increasing intensity, the photoelectric current increases, but do not affect the kinetic energy of emitted electrons. In contrast, when he again performed the experiment with different frequencies higher than threshold frequency, the stopping potential changes and thereby it causes changes in kinetic energy too. Now, the Nobel Prize for Physics in year 1921 is given to Albert Einstein. He gave the successful explanation of photoelectric effect in 1905, led to the quantum revolution in physics and earned Einstein the Nobel Prize in Physics in year 1921. As Planck has assumed that emission of radiant energy takes place in quantized form, the photon, but once emitted it gets propagates in the form of wave. Einstein further assumed that not only the emission, even the absorption of light takes place in the form of photons.
Hello, Tarun again. So let's quickly see the setup used by Leonard to perform his experiment. The special thing about this setup that it is still used today to teach students photoelectric effect. It consists of an evacuated glass tube, a photosensitive plate which is the cathode, which is connected to the negative terminal of the battery. It is also known as the emitter. Here we have the anode connected to the positive terminal of the battery, and here we have the collector. And here we can see the battery. Now we can see the photoelectric effect even without the battery, because when photons strike the photosensitive plate, electrons have gained some kinetic energy due to which they are able to cross this and reach anode and constitute a current. But even if we increase the voltage, then their kinetic energy will increase and the current will increase up to a level after which it will reach a saturation point above which the current will not increase. So here is the quartz window through which light will enter and strike the photosensitive plate. Here we can see the light. Now as the light strikes the photosensitive plate, photons is emitted from it and which constitute a current. Here we can see photons striking and electrons ejecting. Here the value of current is 0.8 ampere. Let's cover some more theory before we move to the experiment. Our first topic is distribution of kinetic energy of photoelectrons. So what happened is that when photons strike the surface, not all electrons have kinetic energy Ke max, where kinetic energy Ke max is given as hf minus work function. In actual, the kinetic energy varies from 0 to Ke max. The loss of kinetic energy happens due to collisions of electron with other electrons. But in virtual simulator, they have taken all electrons to have kinetic energy Ke max. Hence, they have not assumed any loss of energy of electrons due to collision. We will see later in slides that this is one of the errors we will get face when we use the virtual simulator in place of real experiment. The next term is related to the last topic. It is quantum efficiency, which is defined as number of electrons ejected upon number of photons incident into 100%. The maximum value of it can be 100%. Now we will move to experiment part. Basically, we are going to see these three things in the experiment. Variation of photocurrent versus intensity of light, variation of photocurrent versus reverse voltage, variation of maximum kinetic energy of emitted electron versus frequency of light used, and finding Planck's constant from it. In each of the experiment, we are going to use a plate of area 0.2 centimeter square. This is the plate on which we are going to shine the light. So here is our first experiment, seeing the variation of photocurrent versus intensity of light at constant frequency, hence constant wavelength. What the theory says, number of photons in a light beam is directly proportional to intensity of light. On increasing intensity, number of electrons ejected will increase, hence photon current increases, but Ke mass of electrons remains constant at as frequency is constant. Here is the apparatus. We will see it more in detail in demonstration. Let's look at the data we have gathered. As you can see, intensity percentage increase, photo current then increase. You can see this trend from the graph also. We see the same trend for all the four elements. So here it is for sodium. We see the same trend in zinc. We see the same trend in copper. And we also see the same trend in platinum. Let's see the demonstration of the last experiment discussed through virtual lab. Let's select sodium. And as we know that cutoff wavelength of sodium is 504 nanometers, so any wavelength below it will do fine. So what we have observed that when intensity increases, current increases. So we can suppose to see the same trend here. So as you can see, as we are increasing the intensity, you can see the current is increasing. So our experiment is verified. Let's see it for platinum also. Platinum has a cutoff wavelength of 220 nanometer. So we should go to a wavelength below it. So let's choose 160. So now again we will start from 0. So now as we move intensity from 0 to 100%, you can see the current is increasing. Now let's see the second experiment. The second experiment is about seeing the variation of photoelectric current versus reverse voltage. What the theory says, when we apply reverse voltage, electrons are attracted in opposite direction and the current is decreased. There is a certain potential termed as stopping potential at which even the electron of highest kinetic energy, which is given by Ke max, is equal to hf minus work function stop, and current becomes zero. Here is the apparatus. We will see it in more detail in demonstration. We will use source of constant intensity 10 watt meter square in all our following experiments. Let's look at the data we have gathered. As you can see, as reverse voltage increase, current decrease, and after a certain value known as stopping potential, current becomes zero. Here for sodium, we can see the stopping potential is somewhere around 5.8 to 6.9 because during this interval the photocurrent is becoming zero, and we can see it from the graph also that during this period the stopping potential is approximately becoming zero. We can see similar trend for zinc, for copper, and for platinum. Let's see the demonstration of the experiment that we have just studied. So here we have chosen the metal to be copper, whose cutoff wavelength is 751 nanometer. We have taken the wavelength of light used 100 nanometer, so it should show photoelectric effect, and it is showing. As we can see, there's a value of some current here. So now, as when we increase the reverse voltage or make the voltage negative, the current value will decrease, and at some value of voltage it will become zero, and that value will be termed as the stopping potential. So as we can see, it is approximately becoming zero at 7.8. So this is our stopping potential for copper. Let's move to the next part of the experiment. In this experiment, we are going to see the variation of maximum kinetic energy of emitted electron versus frequency of light used and finding Planck constant from it. What the theory says, according to Einstein equation, K is equal to hf minus work function. So if we compare it with y is equal to mx plus c, the slope will give us the value of Planck constant. So we have to just to find Planck constant, we have to draw a graph between kinetic energy and frequency and calculate its slope. Here is the apparatus we will use. We will see it in more detail in our demonstration. Note that we will use 100% of intensity available at Colorado Lab Simulator in all our following experiments. Let us look at the data we have gathered. As we can see that energy versus frequency graph will be a straight line. As discussed earlier, the value of Planck constant will be the slope. The slope can be calculated as taking an elemental length in y direction and dividing it with elemental length in x direction. When we do that, we get the value of h to be 4.1357 into 10 raised to the power minus 15 electron volt seconds. Note that the unit of h here is different from the usual unit. We can see similarly for zinc and for other elements also. We also point to the cutoff frequency here. So you can see that below this frequency there is no photoelectric effect happening. We have also read about and seen this in the initial slides about cutoff frequencies. So below this frequency, no electrons are gaining any kinetic energy. For copper also we have a cutoff frequency which lies between 0.75 and 1.50 into 10 raised to the power 15 hertz, and the value of h is again here coming out to the same, and for platinum also the value of h is coming out to be same. Let's see the demonstration of the experiment discussed earlier. Here we have chosen the element to be sodium, whose cutoff wavelength is 504 nanometer. So when we decrease the wavelength below 504 nanometer, we can see the photoelectric effect happening, and we will see a value of current. So now we have to basically draw a graph between energy and frequency, which is being shown here. So we have to go through all the wavelengths from 504 nanometer up to 0 nanometer. Although it will not show here, but we will still go till here. You can see that the graph is between energy and frequency and not between energy and wavelength. So the wavelength which we are selecting here is getting converted into frequency and then getting plotted. So let's plot it. So as you can see here, after plotting we get a straight line. The Slope will give us the value of h, and here we have getting the cutoff frequency, which is just little bit less than 0.75 into 10 raised to power 15 hertz. Recording.
Hello, this is Prashik, and I am going to explain about error parts in photoelectric effect. Error through experiment observation and analysis, errors are introduced in this mainly due to the factor of least count of instrument. Voltmeter have least reading of 0.01 volt, and micrometer ammeter have least reading of 0.01 microampere. Next, please. Errors which come due to performing in lab and not in real conditions. In actual, when the voltage of battery remains zero, the ejected electrons with zero kinetic energy form a electron cloud near cathode. They have kinetic energy zero due to collision. In this experiment, all the electrons have kinetic energy Ke max. No loss of energy is taken into consideration. As we increase the voltage, the electrons having zero kinetic energy gain some kinetic energy due to the pull of anode and starts moving and the current increases. But the current increases only up to the level after which it becomes constant. As we see the graph of voltage and versus current. As the voltage increases, the current value is also increases. But at some value of voltage, both the current I saturation 1 and I saturation 1 gets to their maximum value, and after that they become constant. This is how the actual graph will look. But while doing the experiment in simulator, current remains same with increase in forward voltage.
Hello, Ravish here. I'm going to cover of usage part of photoelectric effect. Next, photoelectric cell. The photoelectric cell is used in the reproduction of sound which is recorded on movie film. Next. Let's see its working principle. The photoelectric cell is used in exposure meter. The exposure meter is used along with a camera to know the correct time of exposure for having a good photograph. Exposure meter, also called a light meter, photography auxiliary device that measure the intensity of a light and indicate proper exposure for film or image sensor of a specific sensitivity. Next. Camera light meter. On common use of photoelectric effect in a camera light meter, such as those that adjust the automatic iris on various type of cameras. When light strikes the plate in the evacuated tube, it may eject electron. Next. Let's see its working principle. A light meter can read the ambient light in a scene or the direct light from a light source and calculate the correct shutter speed and aperture value required to capture a accurate exposure. These days, nearly all cameras have built-in light meter and a number of modes to calculate exposure setting. Next. Solar cell. The photoelectric effect occurs when electrons are ejected from the surface of a solid material like metal when exposed to sunlight. Next. Burglar alarm. A beam of light shines on a metal electrode in a vacuum tube and causes electron to be electrically ejected from the surface of metal. This electrode thus becomes the cathode. This sets off the alarm system. Next. Photosensor. The photoelectric sensor consists primarily of an emitter from emitting light and a receiver from receiving light. When emitted light is interrupted or reflected by the sensing object, it changes the amount of a light that arrives the receiver. The receiver detects the change and convert into electrical output. Next. Now we reached our end part of presentation. Here is the summary slide. We started with photons and ended with usage of photoelectric effect. In between we see how Max Planck gave hypothesis of radiant energy, how Hertz discovered photoelectric effect by mistake, and Leonard studied the observation made by Hertz, and finally in Einstein came and stated not only emission but also absorption of light takes place in form of photons. Then we performed some experiment to confirm the theory portion was successful. In doing so, we discussed about elimination of virtual lab and finally concluded with use of photoelectric effect. Now I am handing over to Tarun to conclude.
So here are the references that we have used. You can have a look at it. And thanks for watching our presentation. So now as we have reached to our end, let me conclude by a quote from Albert Einstein. And it will be a great timing to mention this because this photoelectric effect is all about Albert Einstein. I mean, he won Nobel Prize for it. Physics is an attempt conceptually to grasp reality as something that is considered to be independent of its being observed. In this sense, one speaks of physical reality. Thank you from all our group.